In this example, we have a ball traveling from player A to player B to player C. So that gives us 3 points, which should immediately have you thinking about drawing a triangle. So our first step here, we're going to decide that up and forward are going to be positive, and then obviously down or backwards are going to be negative. So if we start off by drawing a diagram, we can label it with point A, and this ball is going to go 12 meters at an angle of 30 degrees. So you're going to just kind of estimate your angles here. The closer you draw to the actual angle, the easier it'll be for you when you come up with just checking your answer. So that's going to be 12 meters. And that angle, 30 degrees, is going to be relative to the horizontal. So that angle inside there is 30 degrees. After that, the ball travels 9 meters at an angle of 155. So remember that that's an angle of 155 from your terminal arm. So it's going to be about this way. And this is 9 meters. So your angle of 155 is this angle right here. That's 155 degrees. To find our resultant, we just have to close our triangle up. Remember, we're adding tip to tail. So that's going to be your dr for resultant. Let's take a look at all our x and y components now. So in our first A to B direction, we have an x component here, and then our y component right there. And then for our B to C direction, we have an x component there, and our y component here. If we write out all of the directions that we've dealt with, it will give us a better idea of what we're going to kind of move forward and look to solve. So in our x direction, let's take a look at what we have. So we're going to label this d1x, d1y, similarly d2x, and d2y. So d1x is going to be equal to 12.0, that's the distance the ball was thrown, times the cosine of the angle. That's going to give us 10.39 meters. And that's in the forward or right direction. So we're going to call it forward. Or you could say east or whatever direction you want to use. In our y direction, we have d1y, and that's going to be equal to 12 meters times the sine of the angle. So that gives us 6.0 meters. And if you're looking at your diagram, that's in the up direction. Remember, we're going to decide that forward and up are positive, down and backwards are negative. Now we're on to D2. D2x is 9 meters times the cosine of our internal angle right here, which is 25. That gives us 8.16 meters. If we take a look at our diagram, that's going backwards. So we're going to have to deal with that later when we do some arithmetic. D2y is 9.0 again, but this time it's sine of 25. And that gives us 3.80 meters. And by looking at our diagram, that's in the up direction. We can now go ahead and add up all of our x components and y components. So the sum of all of the x components of our displacement is going to be equal to 10.39 meters plus negative 8.16 meters, because of course it's going in the opposite direction. So our net displacement in the x direction is 2.23 meters And since it's positive, it's going forward. We'll do the same thing for our y's. So the sum of the y's is going to be equal to 6.0 meters. That's up. We'll exclude that from our calculation here. Plus 3.80 meters. They're both positive because they're both going up. That leads us to 9.80 meters in the up direction. Now that we have these components, we can go ahead and draw another triangle because that will give us our kind of resultant triangle here. So let's recall what we came up with. We had decided that our dx, or our resultant dx, was 2.23 meters going forwards, and our resultant dy was 9.80 meters going up. So we can go ahead and draw this diagram. So that's about 2.23 meters forward and 9.0 meters up. This leaves us with a right angle triangle where the hypotenuse is going to be our resultant from the previous question. And we'll have an angle theta in here, which we can also solve for. So remember that dr, our resultant, can be solved using the Pythagorean theorem. 2.23 squared plus 9.80 squared. And after we take the square root of all that, we get a hypotenuse of 10.1 meters. And we can go ahead and use our tan theta, which is equal to opposite over adjacent. So the opposite here is 9.80. The adjacent is 2.23. We can rearrange that to solve for theta. Which gives us a value of 77 degrees. Come up with a final statement. Therefore, the ball's resultant displacement is 10.1 meters, 77 degrees.